Hey, my name is Dominik Bittner, and I would like to talk with you about generating synthetic multispectral images for semantic segmentation in forestry applications. The co-authors are Sean Ferreira, Maria Andrada, Jordan Bird, and David Portugal. Okay. Yeah. First of all, we need to define what semantic segmentation in forestry robotics is. To be able to operate in forestry applications, autonomous robots must be able to perceive the surrounding environment and classify entities according to their task relevance. For example, semantic segmentation, which is in turn the classification of individual pixels. These are supervised models using pre-annotated datasets. But when these models reach their performance limits due to the limited amount of annotated data, data augmentation can extend these datasets to improve the original training. In this case, classes relate to a forest landscaping mission for fire prevention, where life flammable material is the material to remove, trunks and canopies are the plantations to protect, and humans and animals are the wildlife and potential co-workers to avoid for safe operations. Multispectral images, which are coming from the camera mounted on the Ranger, are expected to improve perceptual capabilities when compared to RGB imaging because of specialized filters, in that case the near-infrared channels, which detect chlorophyll and can therefore enhance the plant detection. For example, by using vegetation indices or deep learning methods for semantic segmentation. To augment data, generative adversarial networks or short GANs could be used. These are the composition of two competing networks which are trained simultaneously by an adversarial process to generate new data, where the generator G captures the data distribution without direct access to real data from X, while the discriminator D estimates the probability a sample comes from the training data X or from the generator G. In that case, the generator learns how to replicate the given data from X by interacting with the discriminator D. By feeding random noise Z and potentially other inputs into generator G, the GAN is capable of producing a wide variety of data derived from the target distribution for data augmentation. A specific type of GANs are image translation GANs, which are the conversion of an input image XA from a source domain A to an output YB into target domain B, with the intrinsic source content preserved and the extrinsic target style transferred. If you refer to the previous figure about GANs, this image-to-image translation shown in that figure is constrained or conditional, since it receives a label image X, which can be an outline or pixel-wise annotation. These two figures show a brief illustration of the process. The input image in both figures are separated into their individual components for translation and later to be combined again with synthetically generated parts. In the process, the GAN learns the correlation between original multispectral images and their corresponding near channels. The generator model can then be transferred to translate RGB images into synthetic multispectral images for data augmentation purposes. The following methods were implemented for image-to-image translation. Pix-to-Pix GAN is a conditional pixel-to-pixel translation method, while Pix-to-Pix HD GAN is the first extension with a high resolution and photorealistic image generation. GAN is in turn the extension of Pix-to-Pix HD GAN, where more accurate networks for high precision image generation to avoid washing away the information contained in the semantic segmentations are used. As you can see in the preliminary results, the image translation done by Pix-to-Pix, Pix-to-Pix HD, and GAN is not distinguishable to the ground truth and the input multispectral image. Further, the semantic segmentation using translated images from Pix-to-Pix, Pix-to-Pix HD, and GAN achieved the same result based on visual inspection as in the baseline training or compared to the ground truth annotated by human experts. In the quantitative evaluation, the F1 score, intersection over union, and recall are used as metrics to measure the accuracy of a classifier model, or in that case, a semantic segmentation model. Besides them, inception score and Ferreira inception distance, or short IS or FID, are chosen as common metrics to evaluate the generated images on themselves. The percentage column in the left table provides the ratio of the parameter means of each model as a percentage of the baseline in the first row parameter mean. Besides these numerical evaluations, it should also be considered whether a solution has the potential to improve the images or not, the image generation or not. The results in both tables show marginal differences between each method. As a conclusion, in general, all tested methods provide satisfactory results for the pre-established target. Based on the evaluation results, Gaugen marginally offers the most appropriate solution for future use in synthetic multispectral image sample generation for data augmentation. Future work will focus on data augmentation for semantic segmentation by generating synthetic multispectral images from RGB images taken from a photorealistic forestry simulator, which allows the capability of generating an unlimited amount of training images with ground truth labeling for data augmentation. Thank you for your attention, and if you have any questions, just let me know. I'm happy to answer.
Thank you very much, Dominik. You were able to do it on time. So I would now ask the audience if you have any questions, please shoot away.
With a bit of rush.
Yeah, I have one question. This is my first contact with this technique. I was wondering if there is, if you expect any negative effect of direct sunlight images and in the process, if it would be resistant to this effect or not, to direct sunlight and shadows.
First of all, I need to say in that respect that each part which is in the training images, sure, the GAN network on itself learns as well. So it depends on what you feed into the network. So if you have, for example, bad samples with sunlight or sun reflects in there, your GAN also learns this bias, for example. But to avoid this effect, you can also use first classification of the images to detect the sunlight, so that you can, for example, just use the images which are without sunlight effect. Since as you just think of, if a GAN or that networks is already trained with that samples, it also replicates them. So you cannot remove that effect, but if you classify these images already before the training, you can avoid that effect. So if you have a huge bias in your data set, you can already remove it, or it is suggested to remove the bias already before your training of the GAN to get better results from your GAN training. I hope that answered your question.
Yeah, thank you.
You're welcome.
Any further questions? I also would like to congratulate Dominik, because he recently graduated from his bachelor's in Germany after his visiting period in Portugal.
Thank you.
We're all very proud of you.
Thank you. It was a pleasure. Or it's still a pleasure working with you.
Yeah, of course. And well, if there aren't any further questions, we would end this virtual poster session, and let's wait for the guys at the conference, at the workshop, to synchronize back with them again. Okay. So we'll just keep ourselves here steadily in the Zoom session, okay?
Okay.
Thank you for moderating.
Thank you all, guys.